Welcome to today's webinar, Assuring Continuous High Performance PNT. Solutions for GNSS Challenged or Denied Environments. Brought to you by Loctronix Corporation in cooperation with GPS World. I'm Bethany Chambers from North Coast Media, publisher of GPS World, and I will be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. The recording will be available 2 weeks from today on our website, gpsworld.com/webinars. A link to the on-demand recording will also be emailed to you when it is available. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice in the lower left-hand corner of your console that there is a Submit button. We encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in queue. Many of the questions that were submitted during registration will be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World Magazine or in one of our e-newsletters. We strive to answer as many of your questions as possible. Finally, if you experience any technical difficulties during today's event, please select Help to submit your issue, and Assistant Producer Diane Sofranic or I will personally assist you. Now I'd like to turn today's event over to our moderator, GPS World Editor and Publisher, Alan Cameron.
Thanks, Bethany, and hello, everyone. Thank you for joining us. This is Alan Cameron, Editor-in-Chief of GPS World, and welcome to yet another in our continuing series of professional webinars. This one sponsored by Loctronix on the solutions for GNSS challenged and denied environments. As you probably know, finding position location in challenging environments, of which there are many, is pretty much a watchword or a byword in almost any technical gathering in the industry these days. And Loctronix has some solutions to bring to bear on that. Loctronix is a company whose taglines are locked on location, locating anything everywhere, and as you can imagine, there are some challenges in that. Loctronix provides position sensing solutions for GPS-challenged environments where traditional methods alone are not enough, and their technology has applications in the markets of consumer location-based services, first responder, emergency management, supply chain logistics, urban warfare, blue force tracking, and satellite navigation and remote sensing. We have two speakers today from Loctronix. CEO and founder Michael Mathews and Chief Scientist Pete MacDoran. They're joined on this webinar by colleagues John Taylor from Mercury Data Systems and Tsega Emmanuel from TeleCommunications Systems. I'm going to turn the webinar over to Michael Mathews, and I'll be back toward the end of the webinar to relay your questions to the panel, and you can submit them through the question function on your webinar interface. Without further ado, Michael, please take it away.
Thank you, Alan. Today I'm going to talk about some of the problem domain and some of the solutions that we're bringing to bear to help provide high-performance positioning and navigation and timing in these challenge environments. This will be a lead-off presentation to a discussion in more detail about the specific applications being developed by our partners. Loctronix, when we were founded in 2006, we started with the idea that we wanted to provide PNT solutions for applications that were more than just traditional GPS. We started with the idea that we needed to bring more to the problem now, including multiple sensors and other types of signals, to allow us to develop navigation solutions that would enable us to operate in environments not traditionally supported by conventional GNSS or GPS receivers. Today, the company is developing solutions that not only will provide you positioning and information in challenged environments, but also provide techniques for verifying that GNSS or GPS is actually working correctly or not being spoofed in this case, and as well as providing techniques to mitigate jamming and interference of other types of signals that might be interfering with normal operations. Our company is approaching the solutions developing a software-defined radio-based approach, which we'll talk about here in a second, enabling our partners and users of our products to adapt and develop these techniques for their own applications. This is not a new slide in terms of the industry, but Loctronix' approach for providing high PNT performance positioning and navigation and timing is a multi-sensor approach. Our specific flavor of PNT is to develop positioning navigations at our core using our patented spectral compression positioning technology. And I'll discuss it more in a minute, but fundamentally it allows us to utilize not only GPS and other GNSS type signals, but it allows us to exploit signals of opportunity, including digital television, cellular, and other signals as well for navigation purposes. To that baseline solution, we provide inertial and other types of environmental sensors, including compass, in a multi-sensor fusion approach to deliver PNT that can operate essentially autonomously within a variety of operating domains. Could be space, could be in urban and canyon environments, as well as deep indoors or in cave-type operations. So we view the world essentially as we call our pyramid of sensors. And at the core of that pyramid of technology is SCP. And what is SCP, which I'll be using quite a bit throughout this presentation, is a means for processing radio signals, could be GNSS signals like GPS or other signals like digital television, without specifically demodulating that signal using the designed demodulation techniques. Instead, we provide a nonlinear operation that allows us to do spectral analysis of any intercepted signal and extract from that spectral analysis positioning and timing information that can be used in the PNT problem. Our primary technique of delay and multiply, as shown above, has been used successfully for decades in a technique known as codeless GPS, but we have also applied it successfully now to a variety of terrestrial signals, including the digital television, cellular, 2G, 3G, and 4G signals as well. One of the exciting developments of using SCP technology that we began working on earnestly in about 2008-2009 is the use of that technique to provide Doppler velocity data for the PNT problem. And while Doppler positioning has been used for decades in satellite navigation, we have developed a technique known as Doppler-aided inertial navigation that allows you to measure Doppler speed of a device without knowing the source location of those signals. And this technique has a wide variety of applications, but it's particularly useful in developing speed information that can be used to calibrate inertial sensors in applications like indoor positioning. The technique, essentially, in a brief nutshell, allows us to take a signal using SCP, and from that we can extract velocity information, speed in this case, that allows us to determine, without having to know from where the signal comes, the speed of motion that a device is experiencing. And we can do it with pretty high accuracy. For indoor applications, we have a technique known as Doppler broadening that allows us to measure through the ambient multipath the actual speed of motion of a device in its local environment. And so in this way, we can actually exploit some of the techniques that have been a real challenge for RF operators, the multipath environment. The goal for the Doppler technology is to minimize infrastructure requirements. That in all of our conversations and all of the approach of our solutions at Loctronix, we're trying to develop solutions that minimize the requirement for heavy infrastructure. And when I mean by heavy infrastructure, that's the establishment of additional positioning reference points in RF space that require timing and other positioning almanacs that would have to be distributed and supported through some sort of infrastructure. Using the SCP techniques that I was describing previously, you can achieve 10 centimeter per second better accuracy with their Dane techniques, which in terms of calibrating consumer-grade MEMS inertial sensors can deliver a positioning performance that achieves better 2% drift rate. Some of the products that Loctronix is developing with these technologies focus on the specific niche markets in military and aerospace. Our advanced software radio line of products is a way of delivering these technologies in a form factor that makes it easy for partners to not only test and integrate, but adapt to their specific applications with relative ease. Loctronix this September will be announcing the first of these products, and it's our ASR 2300 multiband transceiver module, which provides the ability to acquire multiple signals of opportunity, including GPS or other GNSS signals, in the frequency range from 300 megahertz to 3.8 gigahertz. Through this module, we can apply a variety of SDR waveforms that the company is developing, including hybrid GPS, a Dane module, and other modules providing signal interference and detection to deliver a variety of PNT and other types of information, namely, is this signal being spoofed or not, for niche market opportunities. This will be available probably for purchase by October 1st, and we would be happy to work with any companies interested in doing so beyond that. One of the opportunities, just a quick blurb about the SDR platform, is that we have found that in delivering our technologies that we needed to create a solution set that allowed companies to quickly and without much complexity adapt our technology to their implementations, which may be on another software-defined radio. The waveform component architecture is a lightweight framework that we've developed that allows portability of any waveforms in our technology to other devices with a minimum of adaptation and implementation requirements, integration requirements. Shortly after launch, we'll be offering our hybrid GNSS receiver, which does two things. This receiver is actually a conventional GPS and GNSS receiver, but it also incorporates our SCP technology, making it possible in a very small form factor to exploit multiple bands of the GPS, including L1, L2, and also multiple channels within the GPS, not only the CA channel, the C channel, but the PY channel as well, and the upcoming M code on L5 as well. This receiver will provide performance capabilities not available in conventional techniques, particularly in signal authentication and validation, but as well as providing robust positioning and performance in a form factor that actually rivals that of lower cost solutions. With SCP hybrid technology, we can develop solutions like enhanced AGPS that utilize the military precision of the GPS receivers, providing performance that easily outstrips normal conventional GPS receivers. In this case, we're showing a comparison between SCP technologies using P-channel GPS, delivering sub 1 to 2 meter performance consistently versus a traditional CA receiver. Another application that we'll also be offering through our partners is our MEP technology, and it provides techniques using the Doppler inertial navigation that I spoke to previously to deliver the indoor positioning capabilities using signals of opportunity. We can talk about this more later in our Q&A. This picture here shows a positioning navigation of indoor positioning at Mobile World Congress last year using nothing more than cellular signals and inertial sensors. Finally, I'm going to hand the presentation off now to, I think John Taylor was up next, to provide our solution for detecting and validating interference and quantifying the veracity of the received GPS and GNSS signals. Using SCP technologies and signals of opportunity, we can provide comparative testing of GPS and other GNSS signals with that of local ambient signals to determine if those signals are authentic. We can also compare signals within themselves to verify that they have not been manufactured and provided in case of spoofing. We can go into that here in the Q&A session if there are questions. So at this point, I would like to hand off the presentation to John Taylor. John.
Hello, everyone. Hopefully you can hear me. I'm John Taylor. I'm president of Mercury Data Systems. We've been working with Mike for a couple of years now and looking to integrate some of his solutions. We should be starting some of that work very shortly. We're mostly focused at this point in time, our company, on developing navigation solutions for personnel, particularly soldiers at this point. And the problem, as the DARPA statement says, I think we all know what the core problems are, is that our warfighters, our military is so dependent upon PNT information in order to conduct their missions. And that's the problem we're trying to solve. Some of the requirements that we have in general are to maintain 3D accuracy of under 10 feet, 3 meters over 24 hours of operation. In some cases, with some of our customers, they're looking for even longer durations for GPS-denied navigation. Everything needs to be real-time, and they want to be able to create maps as they walk through an environment that are accurate. You may have a team that's going in for reconnaissance, and they want to just be able to walk through an environment and relay that information to a tactical team that comes in later. The system needs to be able to operate in both autonomous modes where there's no radiation at all, and in collaborative mode where soldiers can collaborate both for their mission operations as well as collaborate to refine their position estimates. And they want the system to be very, very simple, essentially a green button, red button solution. Just push a button and everything works from there. It can't be anything complicated for the soldiers. So our objectives and what we think are the keys to achieving both surface navigation and subsurface navigation are having a tactical grade MEMS IMU. And this is absolutely a problem area. There just aren't good quality MEMS IMUs that are available and affordable. Having good, robust motion characterization models. I've seen a lot of demonstrations where people are walking around and aren't crawling, aren't sliding on the floor. I was asked a question not too long ago, what happens with your system when a soldier gets into a fist fight? And I said, we've not tested for that yet. The system has to be torso mounted. We've developed both foot mounted and torso mounted systems in the past, but there are distinct challenges in torso mounting a navigation system. It needs to integrate easily with end user devices, for example, the NetWarrior end user device. And our point of contact primarily with Loctronix is on using signals of opportunity. We've worked with a lot of different time of arrival type of ranging systems, and there are just distinct problems with those. You have obstructions, you have multipath, things that cause delays, unpredictable delays that affect the accuracy of the positioning solution.
John, excuse me for just a second. John, it's Alan Cameron. We're getting some comments that people are not hearing you well enough. Can you move a little closer to your microphone or headset and speak a little louder, please?
Actually, I've got my handset up to my face.
Okay.
Yeah. Sorry about that.
Go ahead.
Okay. Let's see. I don't know if I can. Is this louder?
It's clear. It's better. Mm-hmm.
Okay. I probably had the volume down too low on the for the handset. So, okay. Sorry about that, everyone. As an example of a tactical grade MEMS IMU, I'm presenting the Sensinor STEM 300. It's got very, very good bias and ARW numbers. Its rate is good enough. The problem with this system, as you can see, is it costs $8,600. What the military is looking for are tactical grade IMUs that have equivalent performance numbers that are in the $1,000 to $2,000 range. And so there's a big gap in systems that are out there outside of actually the STEM 300 system that's pictured here. I really don't know of any other IMUs that can provide the same level of performance, MEMS IMUs. Going on to talk more about the motion characterization, as I mentioned before, we see a lot of systems that show people walking forward down halls and taking careful steps, but soldiers don't navigate that way. They crawl, they roll over, they go up and down steps, and a lot of other motions. And the motion characterization algorithms have to be very, very robust. It needs to be able to handle any types of motions that a soldier would make during a mission. Again, going back to the torso-mounted IMU, we've done both types of systems in the past. There are definitely distinct advantages that boot-mounted IMUs have with torso-mounted IMUs, but they're not really acceptable in the community. The soldiers don't want wires going up their legs. They actually like to have the entire system embedded in a military radio or some other equipment that they're already carrying. So, the big question here is how to get to a torso-mounted IMU, a torso-mounted navigation system that's acceptable to the military. This is a picture of one of the end-user devices, a NetWarrior system with a display. One of the problems in integrating with that is that it only has a USB hub. They're using common phones that soldiers are used to. The cellular, Wi-Fi, Bluetooth capabilities are disabled. The connection to the radio is USB, and multiple devices have to connect to that, including the navigation system. Okay, and as mentioned, our point of contact with Loctronix is really in the area of signals of opportunity. We'll continue to use time of arrival types of capabilities, but we think the real opportunity for moving forward with a solution for the military is through integrating signal of opportunity capabilities such as the SEP capability that can process military signals as well as other types of signals that are available. They may also be cellular signals. They may be from satellites. And that's where we're working with Loctronix on developing solutions to move forward for warfighter solutions. And this is just an example here of using a multi-GNSS receiver versus using standard GPS. Our findings, whether it's a commercial grade or even a Dagger, is that the receiver capabilities just aren't accurate enough. And using a multi-GNSS receiver, especially one enabled through SCP, will give us more satellites in view, will give us greater accuracy, will give us better altitude accuracy, faster time to first fix, and better coverage overall. And my last slide here is just a reminder of a presentation that was done for GPS World by Don Jewell, I guess a few weeks ago, a month ago, and he identified very clearly in there just what the requirements were for a military system, a navigation system, and they're very consistent. When I saw this presentation for the first time, I thought how aligned our approach to this is with what he's saying is a set of needs for military users. But these are really, really good and well-defined requirements. This is a great roadmap to follow, and I'm glad that Don made this presentation and GPS World presented it. So I'm at the end of my slides at this point in time, and I'll be handing it over to the next presenter.
Pete, go ahead.
Yeah. Thank you, John. My topic relates to the application of the spectral compression technologies for space navigation. The SCP is particularly powerful because it not only exploits the purpose-built systems like the GPS and GLONASS and all of the global navigation satellite systems, but also signals of opportunity. And digital television has been mentioned in this. If you look at the FCC websites involving urban center digital television, they are transmitting sometimes more than 1 million watts of effective radiated power in the UHF band. And and they are signals that are being originated out of quantum electronic-based systems, most likely rubidium oscillators. And that makes a really interesting possibility when it comes to penetrating buildings and so on for the ability to discipline the IMUs. These powerful signals, particularly, they are radiated, of course, to the consumer community, which is near the local horizon. But the antenna patterns are such that the signals that are going off into space are only 10 to 15 dB down from what they are in the toroidal radiation patterns. Because of those high signal levels, they also illuminate out into the cislunar environment, which gives the opportunity for space navigation well beyond the height of where the GPS is. The GPS, obviously, its constellation when it is out there at a distance of 3 Earth radii, and you have geostationary or geosynchronous orbits that are above that. That presents a particular challenge for any of the conventional code correlating receivers, and those challenges have been met, and there's some data at the end of this section showing how well that can do, at least as best can be simulated in terms of all of the signal levels and the Doppler shifts to be encountered. The advanced software-defined radio model 2300 that we're dealing with right now has a hybrid capability that performs code correlation to extract the epoch time, but also to discipline the system by other signals, including those that would come off of cell towers and the digital television. This is kind of a busy slide, but it shows the various realms of low Earth orbit, what can be expected there. These are analytic things right now at 50 centimeters and 12 centimeter per second and so on. If you do it relative to a ground-based reference, you can do very much better at about 10 centimeter on orbit accuracy. And or you could be autonomous out at a geosynchronous orbit and do better than 3 meters and 75 centimeter per second. The digital television, that's an interesting kind of thing because there are a lot of countries around the world where they are using digital television, but the ability to know where they are is sometimes very fuzzy. With the SCP sort of detection approach, as the spacecraft flies over these areas, the receiver goes into a scanning mode and will see the digital television, typically about 6 megahertz wide, and that we can begin to develop the position of that ground-based site when we pass over there, particularly multiple times in the process of the mission. Because we've got multiple bands that we can receive, particularly the L2 and the L1 PY channels, and also we've got the coming M codes, we can extract the ionospheric total electron content to an accuracy of about 0.1 TEC units, which is equivalent to about 1.6 centimeters L1 delay equivalent. And all of this is being done in a size, weight, and power that is suitable for the Space Cube Mini kind of environment, where we're talking about one unit being a cube 10 centimeters on a side with a mass less than 5 kilograms and 1 watt of on-orbit average power consumption. The cartoon here is kind of a summary of the way the orbits look around the world, around the Earth, and we've got digital television going out and illuminating out in the cislunar environment, as well as an interesting place out there, the L2 libration point, at which the Orion space capsule hopefully someday will have a venture out to that kind of distance. The last slide deals with the Spirant simulator involving a spacecraft at a geosynchronous orbit. Over at the left side, these are the simultaneous receptions that are going on of multiple GPS satellites. Many times we're having to receive power levels which come from the side lobes of the GPS transmissions. And in spite of all that, we're able to get some really impressive performance. Part of the magic of that is that we have very long coherent integration times, perhaps out to 100 seconds, as opposed to a typical code correlator, which has to deal with the fact that there's 50 bit per second telemetry coming down. And so the coherent integration time is something close to 20 milliseconds. So we have about a 33 to 37 dB advantage in our coherent integration time, which allows us to get to things like with 100 seconds of coherent integration time to about 3 meters at a geosynchronous altitude. So that's it for my presentation, and now it is to Tsega, Emmanuel. Thank you.
Good morning, good afternoon. This is Tsega Emmanuel with TeleCommunications Systems, based out of Seattle, Washington. The presentation so far has talked quite a bit about the technical components of PNT. What I'd like to do is sort of go more towards the what are the use cases, a little bit more in the commercial and more the consumer and enterprise space. As most of you know, for most of us on the call today, we're spending a good portion of our time, our 24-hour or at least awake time, indoors. Studies have shown that folks are geared more and more towards indoor activities, and in essence, we need to find mechanisms on how we work PNT and location-based services more effectively in an indoor environment. We know that traditional applications of GPS are not effective indoors. As John mentioned, surface and subsurface performance is very different. And in the case of consumer, enterprise, or commercial environments, where we are either indoors, basement, or garages, we are going to naturally come into some challenges with GPS. We're also seeing a growing demand to locate people or assets while in an indoor environment. And the key drivers behind this are really the safety applications, fires, disasters. And then in the retail space, it's more from a consumer perspective, while enterprise has a different slant, but again, the same requirements and the same drivers. And some of these can be, tracking expensive equipment, tracking your workforce, tracking highly valued assets, et cetera, et cetera. And then, of course, the natural desire to extend the usability of on-device applications indoors as well. Typical and high-use applications are navigation and mapping. And as mentioned earlier, I think Michael did, there are additional features and capabilities that are now inherent in these devices. And we want to take those capabilities and leverage you may have heard the term signals of opportunity, capture those and leverage those in terms of location, calculation, and presentation capabilities. Talking about a couple of the use cases, we'll look at some horizontal and vertical use cases. What we're seeing is more and more of location advertising based on end user or consumer location as a fast emerging application or capability. Malls and retail stores are exposing more and more location-based content to their end users or potential end users. Public safety is a huge player in the space as well, more from a safety and disaster preparedness perspective. First responders are looking for better tools to help them get their job done. And we're seeing more and more specific solutions coming into the market, but not consistent across the board. Tracking is a major use case across any of these vertical or horizontal plays. Family tracking is primarily important for children and loved ones. And enterprise, we definitely see workforce tracking as being big, specifically in the dispatch and safety arenas. And every day, or rather, we're seeing more and more technologies coming in with better and improved navigation mechanisms. It's no longer something that is available in vehicles, but it's now inherently available in devices, personal devices that leverage multiple technologies, rather radio technologies that are out there. In the vertical space, healthcare is one of the key drivers for indoor location and tracking capabilities. Tracking medical assets, specifically hardware, as well as personnel. Military, as John mentioned earlier, surface and subsurface tracking, and navigation capabilities required with very little real estate and flexibility by end users. Museum and tours. I think museums and tours were one of the pioneers in providing location-based audio and visual integrations that have excited and really brought in a lot more traffic into that venue. Airports and convention centers are also other key areas where we see adaptation of indoor location from a consumer perspective. Okay. From an ecosystem perspective, in the location-based services arena, we look at who are the players and what are the key elements that need to make the value chain or the ecosystem work together. And the key element here is ensuring that the mapping capabilities are available for indoor solutions or subsurface solutions, that radio networks or signals of opportunities are very well defined and available. And these have to all work with a location server that's going to crunch the data and serve it to an application that is going to present the end user with the relevant content, whether it's mapping, navigation, or some other interaction that's required with the end user. We also look at the capability of extending the smartphone features by adding a thin client or some level of interaction with the device to expose additional features that can then be applied to location capabilities and then extend those to the applicable end users. The other element in here that is referenced is the standards alignment. There are standards bodies that govern quite a bit of the infrastructure and interface requirements, and their alignment and their involvement and engagement is very critical and crucial in the whole ecosystem. Talked about the maps earlier. I'm not going to spend too much time, but just we need to make sure that whatever content we provide, we make it a rich experience for the end user, and also simple and easy to use. Extending the discussion of signals of opportunity, venues. If you're sitting in a mall or if you're sitting at an airport, you're going to see multiple, if you have the capability, you'll see multiple RF sources or radio frequency sources. We have to use these signals as a means into the mechanism that provides a precise, sub-meter type location visibility or resolution to the end user. And these are definitely elements that can be captured. The technology is available. And how do we do that? We basically leverage, existing network coverage. If needed, we augment with in-building distributed antenna systems, microcells, Wi-Fi rather, which is dominant today, or femtocells or small cells as it's now called in the industry. Provision the location servers with rich data, give them the enhancement and processing power, and make the deployment models and service capabilities or the service layer quite easy and seamlessly implementable in existing environments or in greenfield venues as well. We also look at device-based options, at least in our industry, by taking advantage of what's available on the device. Today, devices are very, very smart. They offer, among other things, sensor-based or sensor sets that expose quite rich data, and we need to take advantage of that. With all that combined into one huge amalgamated crunching mechanism or location server, I think we can make the experience very richer and much more rewarding for the end user that is consuming the data and using it for an application for either enterprise, consumer, safety, healthcare, et cetera, et cetera. Just to give you an example of some of the areas that we're looking at in terms of location applications, we have, if we look across the landscape of multiple applications, workforce location is an enterprise application that is used either in medical field, enterprise, as well as public safety. Asset locator is primarily, where the use cases here are primarily in hospital and consumer, but these can be interchanged or applied to various other use cases very seamlessly with integrated applications that and APIs that expose data and content much more seamlessly today than if we went back 5 or 10 years ago. Moving on, I think we're done. Do we go to questions, Alan?
Yes, thank you. And thank you, everyone, for your very comprehensive presentations. The audience is showing a lot of interest in various aspects of this, and I'm going to pass to the questions now. Our first question comes from someone who asks, please discuss multi-method high-accuracy PNT as provided by your solution for intelligent transportation systems and other very wide area applications covering large metropolitan and rural markets, or even entire nations. I'm going to add a little bit of interpretation, or I'm guessing the intent of this person's question is, can you discuss how this works when you're tracking or seeking to position something that's moving at a high rate of speed, for instance, a vehicle on a highway that may pass beneath an underpass or into and out of a tunnel, or in some other way be getting a signal, be obstructed, be getting a signal again, all in a very rapid sequence of events. That question would be for anyone on the panel.
This is Mike Mathews. I'll take it up as a start. The kind of boiling that down, the question is, can we do these techniques for rapidly moving vehicles using signals of opportunity? The essential challenges for intelligent vehicle systems, or even navigating in a car in general when you have obstructions coming in and out, is how do you maintain accurate positioning information when GPS is sporadic or it's not available constantly. In general, GPS will degrade in those urban environments where you might see one or two GPS satellites constantly, and in certain cases, like going through a tunnel, you may not see anything. In those cases, SCP technology and even DANE technology can be applied to enhance the discipline and constraints of commodity-grade MEMS sensors to maintain a flywheel effect in twofold. A, it maintains oscillator discipline, so it allows you to reacquire and coherently reconnect the pseudo ranges that you might get from GPS, enhancing the ability to track through those issues with more consistency. But in addition to that, you can leverage the relative ranging information off of DTV and the inertials to actually provide you with navigation information while the GPS is being sporadic. In general, even at high rates of velocity, you can maintain good levels of performance. We're not specifically testing that right now in our shop, but definitely have seen cases of that on our orbital simulations that we do all the time, where GPS is coming in and out of operation.
And that's a really high speed.
Yeah. I'll throw it over to others on the panels if they have other comments as well.
This is Pete MacDoran. When we're on orbit, we're talking about speeds up there that are around 7 kilometers per second.
So that's really high speed.
All right, passing on to the next question posed from the audience. Someone wants to know, how soon will Loctronix technology be available for smartphones to give reliable 2-meter accuracy in deep urban canyons? I think that, if I may add an interpretation here, I think the question actually has 2 points. One, the form factor to fit in a smartphone and other considerations that would bring to bear on a smartphone platform. And the other, of course, would be price. Is it going to be affordable anytime soon, or how far in the future for that kind of platform where, of course, mass market cost is an often overwhelming factor? Gentlemen?
Yeah. This is a question that perplexes my board of directors almost every month. How long before mass market opportunities will be available to Loctronix? The short answer is that right now we're working on an MEP, our Mobile Explorer platform solution. We're getting ready to deliver a version of that to TCS for them to work with. We don't have release dates where they might incorporate it into their products yet. But the short term for our technology is actually focused on niche vertical markets that are capable of using not necessarily consumer-grade electronics. The challenge of going after the smartphone market is basically that we would have to embed our technology into the baseband radios that are available on those phones. And that proves to be a very long process, and one where you have to demonstrate to those technology providers that your technology is ready for mass market commercialization. This will take some years to prove out, ultimately, in our plan. So I wouldn't expect to see things like SCP and Doppler-aided inertial navigation inside a smartphone in the short term. But you may see it in specialized devices, and that's where we're focusing. When we launch our initial SGR engine, that should be available for $1,500 for developers who are interested in starting to use these technologies in their own testing and prototype implementations. But for large-scale consumer applications, it will be some time yet.
All right, we have another question. Oh, did somebody else from the panel want to throw in a comment?
I was just asking that, Alan. Apologies.
Okay. Here's another question from the audience. It's very interesting to hear about a company commercializing usage of SOOP. This topic is discussed usually in academia. Generally, the power consumption and cost make these systems out of reach. Here we're kind of circling back to portions of the previous question. But somebody, again, is posing the question, what's the cost? I think I heard a $1,500 tag on basically a development kit, if I understood correctly. Can you explore that a little further, and also the question of power consumption?
Sure. This is a relevant question in the fact that the architecture that we're approaching to get our technology out there is software-defined radio. And in general, this is a very programmable technology that allows you to take a generalized piece of hardware and apply it for a specific, you can program it for it to do what you'd like it to do. These systems traditionally have been, they consume more power than we would say it may be a corresponding purpose-built ASIC solution where you can optimize the design to remove as much power consumption as you can. In the markets that we're focusing on, we see opportunities to utilize software-defined radio technology. The cost is definitely not what I'd call consumer grade at this point, but commercial grade applications we can definitely reach. We can definitely reach military and space applications using this approach. And the power performance, when we manage the power very effectively, we can hit form factors that are power consumption models that are actually acceptable in these niche vertical markets. I think in terms of cost and power consumption for consumer markets, you're right that there's still a ways to go. Anybody else want to comment on that?
All right. Before I move to the next question, I've pushed out the slide that gives contact information for our speakers. If anyone in the audience wants to follow up with them after the webinar, I should mention that this webinar will also be posted to our website within 2 weeks' time. And I found it so interesting, I'm going to try and capture or repurpose, as we say in the publishing trade, some of the content for an appearance in either GPS World magazine or one of our email newsletters sometime in the near future. Let's go to the next question. Somebody wants to know, will technology such as this eventually get us to a point where we no longer need space-based PNT?
I'll try that one. This is Pete MacDoran. Well, I sort of think about our planet being kind of mostly surfaced by water. And what we're talking about here with signals of opportunity are particularly related to, urban centers and so on. But there will be space-based systems that really are best to cover, mountainous terrains and oceanic surfaces and so on. And it's going to be hard to get away from that. Now, we're going to see probably variations that will be somewhat different than the way that the current GNSS systems are implemented in terms of fairly big spacecraft and so on. And it could be that there will be signals of opportunity that are space-based that will end up being, in essence, methods of contributing or augmenting the space-based things that we now know as the GNSS.
All right, thank you, Pete. I'm going to pose one final question and also alert the audience that we're nearing the end of our webinar. We have a couple of minutes left. If you want to get in that last question, please send it in. Here's our final question as we stand now. Please give an opinion about how current radio frequency spectrum can handle the increase of down data to the user.
Wow, that's an interesting concept in itself. We could devote a whole hour to how you maximize RF spectrum. Tsega, please feel free to jump in on this one if you've got some comments. But in general, you know, we as a company are pushing the idea of autonomous positioning. We want our devices, to the extent possible, to have all the sensor and information they need to do positioning and navigation on their own. Because we don't believe that ubiquitous 24 hours a day, all available all the time communications is going to be a realizable thing in all environments for some time to come. Pushing data down to the device, it could be map data, it could be almanac data for the positioning and navigation problem. The amount of information that this is compared to other types of data, such as video and audio streaming, you know, Netflix and those other sorts, is relatively small. I think this question, if you are in regards to talking about the size of the streaming of Netflix, that's where we get into how RF spectrum can handle the communications infrastructure. I, like probably most other users, am very interested to see how the major communications organizations will handle that as multimedia content begins to really increase the demand on our RF spectrum. I do think, however, in terms of the PNT problem, the types of information that we need to move around the network and provide probably will not overly tax the communications infrastructure and should allow us to continue moving forward. It's just how do we coexist with those bigger streaming services is, I think, one of the big questions.
Yeah, just to add to that, Michael, I think you captured very, very effectively. Even today, the status quo, that we leverage as much as possible infrastructure and mechanisms that are able to handle very little data payload with maximum efficiency and throughput. So in terms of moving forward and the evolution of taking signals of opportunity and bringing them into the ecosystem, we see that as taking place with the same mechanisms today, with very little to minimal impact, if none, to the key highways that are used for data, for voice, or other features and services that are coming down the road. So, with the capability of storing data on the device, as Mike mentioned, extended ephemeris or some orbital data for a period of time for device consumption or application consumption that's refreshed. When we look at these implications and applications, we look at the power consumption requirements and the footprint requirements, and we continue to optimize those. So, impact little to none as we go forward.
One final question, gentlemen. You won't have seen it in your in our communication function because it just came in. I'm just going to ask it over the air. You discussed using Doppler effects of SOP to determine velocity. What is the lowest speed that can be detected? That is this suitable for walking?
Yes, actually, we developed the technique for pedestrian navigation. That was a primary goal that we actually were messing around with our technology initially in our labs, and we noticed as we walked down the hall, we'd see these effects. The lowest speed that we typically track right now, it depends on how you configure your device, but in general, we've put a threshold on our receiver at about 15 centimeters per second. That when you get below that, we typically see a lot of noise. Now, it depends on the profile of the user. If the user is not undergoing high rates of change in their motion profile, we can increase the sensitivity of the receiver to actually go below that threshold. But for normal pedestrian navigations, we tend to put the floor around 15 centimeters per second.
Just to kind of give you a gauge, at 15 centimeter per second, that's the bridesmaid moving down the aisle speed.
Oh, probably half that speed. It's really hard to move that slow as a pedestrian.
All right, gentlemen, I want to thank you all for appearing on this webinar and thank our audience for attending. We've heard from Michael Mathews, CEO and founder of Loctronix, John Taylor from Mercury Data Systems, Pete MacDoran, Chief Scientist of Loctronix, and Tsega Emmanuel from TeleCommunications Systems. Once again, the webinar will be available for download if you would like to listen to it again, or if you'd like to share it with colleagues. It will be available for download on our website within 2 weeks' time. This concludes our webinar. I'm Alan Cameron from GPS World, and thank you so much for attending. Back to our session controller, Bethany.
Yes, thank you again for attending. Please join us for our next GPS World webinar, GNSS Industry Outlook 2014, on Thursday, August 15th at 1 p.m. Eastern Daylight Time. Alan will again be moderating, and that will be a discussion between several veteran industry analysts. We look forward to seeing you there, and have a great afternoon.